The P versus NP problem is perhaps one of the most notorious problems in computer science and mathematics today. If you manage to solve the P versus NP problem, you could win $1 million prize. So let's dive in. So what is the P versus NP problem? Well, P stands for polynomial time and NP stands for non-deterministic polynomial time. Let's consider a jigsaw puzzle. If you have an efficient way to solve it quickly, like always knowing exactly where each piece goes, that's P. These are problems where a solution can be found quickly in polynomial time, meaning as the size of the puzzle or problem grows, the time to solve it doesn't go out of control. For example, sorting a list of numbers is a P problem. Now imagine that someone gives you a completed puzzle. You can check if it's correct in no time. NP, non-deterministic polynomial time problems are those where if someone gives you a solution, you can verify it quickly. But finding that solution in the first place might be super hard, like scrambling around looking for where each puzzle piece goes. So this boils down to the key question: can every problem we can verify quickly also be solved quickly? In other terms, is P equal to NP? Well, if you could prove P is equal to NP, great, you're on the verge of becoming a millionaire. But it's not that easy. If we can prove it, then we can solve hard problems such as cryptography and encryption. So why is P thought to be a subset of NP? Well, every problem in P, so problems we can solve quickly, is also in NP, because if we can find a solution quickly, we can obviously verify it quickly too. In fact, the verification process might be even easier than finding the solution. But not every problem in NP is in P. That's the mystery. There are problems where verification is easy, but we don't know if solving them is easy. So, moving on. Polynomial time means the time to solve a problem grows at a manageable rate as the input gets larger. Think of it like this. If the puzzle grows, you can still solve it with a predictable amount of effort. Exponential time means the time to solve grows crazy fast as the input grows. Adding just one more piece makes it way harder to solve. So, when we say a problem can be solved in polynomial time, we're saying it's efficient. In NP, we don't know if the solving part can be done efficiently. We just know the verifying part can be. So, why is Sudoku NP? Well, if someone gives you a completed Sudoku grid, it's easy to check if it's correct. It's just a matter of scanning the rows, columns, and grids. That's the essence of NP. Easy to verify. However, finding a solution for an unsolved Sudoku puzzle, especially as it grows to larger sizes like 4x4 or n×n grids, this can be much more difficult. We don't have an algorithm that can solve it quickly for every possible puzzle. It takes time and trial and error. So, Sudoku belongs to the class NP because its solution is easy to verify, but finding the solution is potentially hard. But here's where it gets more interesting. NP complete problems are the hardest problems in NP. If you solve one NP complete problem in polynomial time, so let's say Sudoku, then every other NP problem, including things like Hamiltonian cycles, traveling salesman problem, or SAT, can also be solved quickly. Cook's theorem shows that the SAT problem, or SAT, checking if a logical circuit can be made true, is NP complete. This means all NP problems can be reduced to SAT, and if we can solve SAT quickly, we can solve every NP problem quickly.